Hi to you all, I'm Pascal Antonis from Tilburg in the Netherlands. This lesson is for week 1, Introduction to Music Production at coursera.org. I will be teaching how to visualize sound and understand it in a DAW.
There are 3 good ways of visualizing sound in a DAW. The oscilloscope, the spectrum analyzer, it's over here, and the sonogram. The oscilloscope represents the compression of sound. Sound propagates in the air as a longitudinal wave, where the direction of vibration is parallel to the directional propagation. Note that in the oscilloscope it is visualized as a transverse wave, where the direction of movement isn't parallel to the directional propagation. Here you can see the amplitude of a sine wave. And this is a sawtooth wave. When the amplitude gets more variation on the vertical scale in the oscilloscope, it means that in the real world the air will get more pressure variations or more voltage variations in a cable-wire. The air particles actually compress more and the longitudinal waves will get denser. We perceive it as a louder sound. The opposite is called rarefaction. A lower amplitude on the computer and less pressure variations in the air. On the horizontal scale there is a time indication. When I freeze the wave while playing A3, you can see it has 5 peaks in this time period. When I play A4, it has 10 peaks. It means that the frequency is doubled, so when I go up an octave, the frequency doubles. We perceive it as a higher pitch. The computer measured it as frequency. A spectrum analyzer shows vertically the decibels in full scale, or in short dBFS. It goes from minus 60 dBFS to 0 dBFS. Here you can see the amplitude of a sound. Horizontally it shows the frequency spectrum. When I play A3 as a sine wave, you can see it has a frequency of 220 Hz. When I play A4, you can see it has a frequency of 430 Hz. Now you can see in digits the frequency is doubled when you go up an octave. So 220 Hz, A3, A4, 430 Hz. Note that the spectrum analyzer shows one frequency as a sort of very small mountain peak with energy around it. This is a limitation because it only has energy at one frequency. When I lower the volume, the amplitude goes down, less decibels. When I raise the volume, the amplitude goes up, more decibels. Now I'm playing A3 as a sawtooth wave. Can you see and hear what happens? Still playing A3. This is the fundamental note. All these peaks are integer multiples of the fundamental note. Times 2, times 3, times 4, times 5, etc. There is energy at more frequencies, so the sound changes. This is called a timbre change. Note the further we go up in the frequency spectrum, the less energy it has. But the fundamental note isn't really affected in amplitude or in frequency by the timbre change. A fun fact to see when you combine a sine and a sawtooth wave, only the fundamental note, A3 in this case, changes in amplitude. This is a good thing to know when combining waveforms to make leads for your music. And finally, the sonogram represents the change of timbre, frequency and amplitude over time. Vertically there are frequencies, horizontal there is time. The amplitude can be seen by the blue color. The higher an amplitude, the more intense the color will get, and the opposite. When I go from A3 to A4, you can see what happens with the blue color over time. When I change the sine wave to a sawtooth wave, you can also see the energy at multiple frequencies. It gets interesting when I play different notes. You can see that different notes don't have energy at the same frequencies.